Write an exact equation including the stretch factor for each polynomial below. For 5 and 6, we've got graphs, and for number 7, we've got a sentence containing some information about a polynomial. So let's start with number 5. This is kind of the opposite of what we were doing on the previous slide, where we were taking the equation and drawing rough sketches. Now we're taking the exact graph and we're creating exact equations. Okay. We've got x-intercepts at 0, 0, and at 3, 0. So I know that my equation should contain an x because of the x plus 0, and an x minus 3 because of the 3, 0. Keeping in mind that the positive 3x intercept results in an x minus 3 factor, right? That opposite sign. Any bouncing or flattening out, we do see that here at 0, 0. That means that we've got a double root at 0. So that factor needs to be squared. So that's going to be x squared. We also have to account for a possible stretch factor. We did this in lesson 813, where we were writing in an a value and then solving for it by taking another point on the graph and plugging that in. And that's what we're going to do with the 2, negative 8. We're going to take that point, plug it in for x and y into this equation that we've made to find that a value. So I'll do that off to the left here. So we've got y, again, y equals a x squared times x minus 3. I'm going to plug in negative 8 for y and positive 2 for x. It doesn't matter what point you plug in from the graph, but this one's labeled, so we can use that one. Let's simplify and solve for a. Negative 8 equals a times 4 times negative 1. So negative 8 equals negative 4a. Divide both sides by negative 4 and we get a equals 2. So we can take that and plug that in for a. There's our equation. Y equals 2x squared times x minus 3. Again, and what that 2 does to our graph is it vertically stretches it, so it is important to have it as part of our equation. Okay, number 6. We've got roots at 2, 0 and at 1, 0. So my equation is going to have in it an x plus 2 and an x minus 1. At negative 2, 0, the graph goes right through the x-axis, but at 1, 0, the graph does flatten out. Notice this like flat part here. So that's going to be a triple root, which means that the x minus 1 has to be cubed. Again, we have to find out what that stretch factor is. We'll fill in an a, pick a point from the graph, and plug that in. So we'll plug in 0, 1. Plugging in 0 for x and 1 for y. Do that off to the side. Okay, again, plugging in 1 for y, 0 for x. Simplify and solve. We get 1 equals a times 2 times negative 1 cubed is negative 1. So 1 equals negative 2a. A is just negative 1/2. So that is going to be compressing our graph. Okay, let's plug it back in to our equation now that we know what a is. And there's our exact equation. Okay, same deal for number 7, except for number 7, we don't have a graph. We're just given this description here, but that's still enough information to be able to do the same process. So 7 says a graph that passes through the point 1, 56 and has roots at negative 3, 0, 2, 0, and 5, 0. Notice that there's no mention of any bouncing, any flattening out on the x-axis, so we don't have to worry about squaring or cubing any factors. Our factors are just going to be x plus 3, x minus 2, and x minus 5. But again, we do have to figure out what that a value is, what that stretch factor is. We do have a point here to plug in, 1, 56. So we'll plug in 56 for y and 1 for x. So that's going to be 1 plus 3 times 1 minus 2 times 1 minus 5. 56 equals a times 4 times negative 1 times negative 4. Okay, this is going to be positive 16a. A equals, we'll divide 56 by 16. That is going to be 3.5. So a little messy here, but I'll just plug that in at the top here. 3.5 for A. And there is our equation.